welcome back. Wherever you are right now, however you are resting, let the day fall away. Tonight, we are going to leave this world behind for a little while. Not far, just upward. On a clear night, far from the lights of any city, you can look up and see thousands of stars, tiny distant points of light, scattered across the darkness, like the remnants of something vast and beautiful that shattered long ago. And in a sense, that is exactly what they are. Every single star you have ever seen in the night sky has a story, a beginning, a long and burning middle, and an end so dramatic, so extraordinary, that it strains the imagination to contain it. Tonight, we are going to follow that story, from the very first breath of a star to its final magnificent death. And along the way, we will discover something quite remarkable. That the story of the stars is also, in the most profound and literal sense, the story of us. So let yourself settle. Let your breathing slow. Let the darkness behind your eyes become, for a moment, the darkness between the stars. And let us begin. Every star begins in darkness. Not the comfortable darkness of a bedroom at night, but the vast, cold, almost incomprehensible darkness of deep space. A darkness so complete, so total, that it makes the darkness behind your closed eyes feel warm and intimate by comparison. Scattered across this darkness are enormous clouds. Not clouds like the ones that drift across our sky on a grey afternoon, but clouds made of gas and dust, hydrogen, helium, and the remnants of stars that lived and died long before our own sun was born. These clouds are called nebulae, and they are quite simply some of the most beautiful structures in the known universe. If you have ever seen the Pillars of Creation, that famous image captured by the Hubble Space Telescope, you have seen a nebula, towering columns of gas and dust, lit from within by the light of newly forming stars, glowing in shades of amber and blue and deep, impossible violet. It looks like something dreamed. For millions of years, a nebula simply drifts, slowly, silently, spread across distances so vast that light itself takes years to cross them. But then, something happens. Perhaps a nearby star explodes, sending a shock wave rippling through the cloud. Perhaps two regions of the nebula drift close enough to feel each other's gravity. Whatever the trigger, the cloud begins to change. Slowly, almost imperceptibly at first, it begins to collapse. gravity, that most patient and persistent of forces, begins to pull the gas and dust inward, toward a center, toward a point. As the cloud collapses, it heats up. The atoms within it move faster, collide more frequently. The temperature begins to rise. Over hundreds of thousands of years, a dense, hot, spinning core forms at the heart of the collapsing cloud. Scientists call this a protostar, a star in waiting, a star not yet born, but becoming. And at the center of this protostar, the temperature climbs 10,000 degrees, 100,000, 1,000,000, 10 million degrees. And then something ignites. At the heart of the protostar, under conditions of almost unimaginable pressure and heat, something extraordinary begins. Hydrogen atoms, the simplest atoms in the universe, each one just a single proton with a single electron, are being crushed together with such force that they begin to fuse. This process is called nuclear fusion, and it is the most powerful energy-releasing process in the known universe. When hydrogen atoms fuse, they create helium, and in the conversion, a tiny amount of mass is transformed directly into energy. Pure, radiant, almost incomprehensible energy. This energy pushes outward, against the relentless pull of gravity pushing inward. And in this balance, this extraordinary delicate equilibrium between the force that would crush the star and the energy that would expand it, a star is born. It begins to shine. Think about that for a moment. A star is, at its heart, a constant balancing act, a perpetual conversation between gravity and energy, between collapse and expansion, between darkness and light. And this conversation, this negotiation between opposing forces, can last for an almost inconceivable length of time. Once a star ignites and settles into its hydrogen-burning phase, astronomers say it has entered what they call the main sequence. This is the long, stable, middle period of a star's life. Our own sun has been on the main sequence for approximately 4.5 billion years, and it will remain there for roughly another 5 billion years more. 5 billion years. Let that settle. The entire history of life on Earth, from the first single-celled organisms in the ancient oceans, to the dinosaurs, to the first human beings, to this very moment, has unfolded in less than 1 billion years of our sun's main sequence life. We are, in cosmic terms, a very recent development. The size of a star determines how long its main sequence lasts. Smaller stars, called red dwarfs, burn their hydrogen so slowly and efficiently that they can remain on the main sequence for trillions of years, far longer than the current age of the universe. Larger stars burn hotter and faster. A star 10 times the mass of our Sun might exhaust its hydrogen in just 20 million years, a mere blink in cosmic time, before moving toward a far more dramatic end. Eventually, every star begins to run low on hydrogen at its core. The fuel that has kept it burning for billions of years begins to thin. The balance between gravity and energy starts to shift, and the star begins to change. For a star like our Sun, this change is profound. As the core contracts and heats up, the outer layers of the star begin to expand, to swell, to grow. The star becomes what astronomers call a red giant. When our own Sun reaches this stage, in approximately 5 billion years, it will expand so enormously that it will swallow the planet Mercury, then Venus, and quite possibly the Earth itself. The oceans will evaporate, the atmosphere will be stripped away, the surface of the Earth will become molten rock. But do not let that trouble you tonight. 5 billion years is a very, very long time. And whatever humanity becomes in that span of time will be utterly unrecognizable from what we are now. Inside the red giant, extraordinary chemistry is taking place. As the core contracts and temperatures rise further still, the star begins to fuse helium, the ash of its former hydrogen burning, into heavier elements. Carbon, oxygen, nitrogen. These are not abstract chemicals. These are the building blocks of life itself. The carbon in your body, the oxygen in your lungs, the nitrogen in your DNA. All of it was forged inside a dying star. The astronomer Carl Sagan once said that we are made of star stuff. And he was not speaking poetically. He was speaking literally. Every atom in your body, heavier than hydrogen, was created inside a star. You are, at the most fundamental level of your existence, the recycled material of ancient suns. For stars of our Sun's size, the end comes relatively quietly. After the red giant phase, the outer layers of the star drift away into space, slowly, beautifully, forming a glowing shell of gas around the dying core. Astronomers call this a planetary nebula. What remains at the center, once the outer layers have drifted away, is the hot, dense core of the former star, no longer fusing, no longer burning, simply glowing, cooling, fading. This remnant is called a white dwarf, roughly the size of the Earth, but containing the mass of a star, A teaspoon of white dwarf material would weigh approximately 15 tons on Earth. Over billions of years, the white dwarf slowly cools. Eventually, it will cool completely into a cold, dark, invisible cinder. A black dwarf, the final, quiet, resting state of a star like our Sun. But not all stars go quietly. For the most massive stars in the universe, those with 10, 20, 50 times the mass of our Sun, the end is something altogether different. Something so violent, so luminous, so extraordinary, that it can briefly outshine entire galaxies. These stars live fast and die spectacularly. After exhausting their hydrogen, massive stars become red supergiants. Stars so enormous that if one replaced our Sun at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Inside these supergiants, the nuclear furnace works through the elements with increasing speed. Helium fuses into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage of fusion releases less energy and takes less time than the last. What took billions of years for hydrogen becomes millions for helium, thousands for carbon, and just days for silicon. Until finally, the core fills with iron. And iron cannot be fused. Iron does not release energy when fused. It absorbs it. Iron is, in a very real sense, the end of the road for a massive star's nuclear furnace. The fire goes out. What happens next occurs in a fraction of a second. Without the outward pressure of nuclear fusion to support it, the iron core collapses, catastrophically, instantly. In less than a quarter of a second, a core the size of the Earth compresses to a sphere just 20 kilometers across. The density becomes so extreme that electrons are forced into protons, creating neutrons. The core becomes essentially a single enormous atomic nucleus, a neutron star. The outer layers of the star slam into this impossibly dense core and rebound. An unimaginable shockwave tears outward through the star at a significant fraction of the speed of light. The star explodes. This explosion is called a supernova, and it is one of the most violent events in the known universe. For a brief period, days, sometimes weeks, a supernova can release more energy than our Sun will emit in its entire 10 billion year lifetime. It can briefly shine with the light of billions of suns. An entire galaxy can be outshone by a single dying star. And in the chaos of that explosion, something remarkable happens. The violent conditions create elements that no star's furnace could ever forge in peacetime. Gold, silver, platinum, uranium, the heaviest elements in the universe, born in the death throes of a massive star. The gold in any jewelry you own, the silver in any coin, all of it forged in a supernova explosion billions of years ago, in a star that no longer exists. Some remnant cores become neutron stars, impossibly dense, 20 kilometers across, but containing more mass than our sun. Some neutron stars spin hundreds of times per second, emitting beams of radio waves like cosmic lighthouses. These are called pulsars. When astronomers first detected them in 1967, they briefly considered the possibility of signals from an intelligent civilization. They named the signal LGM-1, Little Green Men. For the most massive stars of all, the core continues to collapse past the neutron star stage, into something from which nothing, not matter, not light, not anything, can ever escape. A black hole. A point of such extreme gravity that space itself curves infinitely around it. A place where our understanding of physics reaches its limits, where the known laws of the universe simply stop applying. But the story does not end with the explosion. The material expelled by the supernova, all those elements forged over billions of years inside the star, drifts outward into space, slowly, over thousands of years, mixing with the gas and dust already present in the galaxy, enriching it, seeding it with carbon, oxygen, iron, gold, and all the other elements that were not present when the universe was young. And in time, that enriched cloud of gas and dust begins to collapse under its own gravity. A new protostar forms. New planets coalesce from the disk of material surrounding it. And on one of those planets, perhaps, in the warm shallows of a young ocean, the carbon and hydrogen and oxygen and nitrogen, forged in the hearts of stars that died before the planet even existed, begin to combine in new and increasingly complex ways. Life begins. This is not mythology. This is not poetry. This is, as best as science can determine, what actually happened. The atoms in your body were forged in stars, were scattered by explosions, drifted through space, fell into our solar system as it formed, were cycled through oceans and atmosphere and ancient organisms across billions of years, until eventually they became you. You are not separate from the universe. You are not a visitor to it or an observer of it. You are part of it, made from it, a temporary arrangement of ancient star material that has, for a brief and extraordinary moment, become conscious, become aware, become capable of looking up at the night sky and recognizing in the light of distant suns something of itself. We have traveled quite far tonight. From the cold darkness of a nebula, through the ignition of a protostar, across billions of years of quiet, steady burning, through the swelling of a red giant, the slow fading of a white dwarf, the catastrophic violence of a supernova. And back, always back to here, to this moment, to you. The universe is approximately 13.8 billion years old. Our sun is 4.5 billion years old. The Earth is 4 billion years old. Modern human beings have existed for perhaps 300,000 years. And you, in this particular form, in this particular moment, have existed for just a handful of decades. And yet here you are, a collection of ancient star material, lying in the dark, listening to the story of where you came from. There is something quite beautiful about that, when you let yourself feel it. The next time you find yourself outside on a clear night, and you look up at the stars, perhaps you will feel it differently. Not as distant things, remote and indifferent, but as kin, as ancestors of a kind, as the forges in which you were atom by atom made. For now, though, let the stars wait. Let your breathing slow, let your thoughts grow quiet and soft and distant. You are safe. You are resting. And somewhere above you, through the ceiling and the clouds and the atmosphere and the vast darkness beyond, the stars are burning. As they always have, as they always will. Good night.